Hello, I'm Ahmed Parek, and I'd like to welcome you to the Chapter 21, Activity 18, Enols and Enolate series. If this is your first time with us, allow me to extend a personal invitation for you to get your pencils and pens and OChem along with us each show. And if you've been with us before, allow me to thank you for inviting us back for another series of OChem. To start off, we're going to draw our lone pairs on our oxygen, and using a proton transfer, we'll deprotonate our acid to protonate our oxygen atom. In the second step, we're going to use the acid to deprotonate our alpha carbon so we can move the bond to our cyclohexane and break the double bond of our oxygen.
You know, this is the fun part of this whole technique.
You just bring this lone pair down off the oxygen
and just beat the devil out of them.
This will break our double bond and cause a nucleophilic attack to our electrophile. Then we'll use our acid to deprotonate our oxygen to get rid of the positive charge. In basic conditions, our base will deprotonate the alpha carbon, moving the electrons to form a double bond between our carbonyl carbon and our alpha carbon, breaking our double bond of our carbonyl and moving our lone pair onto our oxygen. Then we'll take our lone pair
and just beat the devil out of them.
And this will break our double bond between our carbonyl and alpha carbons, causing a nucleophilic attack onto our electrophile to give us our final product. For the next question, we will be using acidic condition enol formation and basic condition enol formation to create our enols and enolate products. You can pause the video and attempt to do this now.
Ready to have some fun? Let's do it.
Doc, it's the breathing.
You know, this is the fun part of this whole technique.
Trap shit. Damn, son, where'd you find this?
Beat the devil out of them.
Real trap shit. Damn, son, where'd you find this?
You know, this is the fun part of this whole technique.
Real trap shit.
deprotonate a carbonyl compound, the conjugate acid must have a pKa value greater than 20. So two common bases that we can use are LDA and sodium hydride.
Real trap shit.
The structure of the conjugate acid is as shown, and the pKa of LDA is 36,
Beat the devil out of him.
Real trap shit.
and the pKa of sodium hydride is 35, giving us the value greater than 20 that we need to completely deprotonate our carbonyl.
Beat the devil out of him.
Real trap shit.
Question 4 states that the pKa value of a 1,3-dicarbonyl compound is around 10. So why is the CH bond so acidic? Recall that ARIA is used to determine the stability of a base.
And just beat the devil out of it.
Real trap shit. Damn, son, where'd you find this?
Because I could find freedom on this canvas.
Real trap shit.
The conjugate base is resonance stabilized as shown, and this would explain the acidity of the CH bonds.
Damn, son, where'd you find this?
For
Beat the
question
devil out
5,
of 'em.
for a base to be strong enough to completely deprotonate a 1,3-dicarbonyl compound, the conjugate acid must have a pKa value greater than 10. Is NaOH strong enough to deprotonate a 1,3-carbonyl compound?
Real trap shit.
devil out of it.
As you can see, if you take the NaOH, its pKa is 10, and after you create your enolate and water, and the pKa value of water is around 15. So NaOH is strong enough because the pKa of water is 15 compared to the base pKa of 10.
Damn, son, where'd you find this?
We don't make mistakes. We have happy accidents.
Real trap shit.
For question 6, use what you've learned about 1,3-dicarbonyl compounds to draw the enol.
Damn, son, where'd you find this?
Beat the devil out of it.
Real trap shit. Damn, son, where'd you find this?
Beat the devil out of it.
Real trap shit. Damn, son, where'd you find this?
Halogenation. Under acidic conditions, halogenation occurs only once at the alpha position via a nucleophilic attack by an enol. For question 7, provide a mechanism for the formation of the enol and then nucleophilic attack on the electrophile. We start out by having our oxygen deprotonate our acid.
Damn, son, where'd you find this?
then deprotonates our alpha carbon, which gets rid of our positive charge on the oxygen.
Where'd you find this?
Following that, we have our lone pairs kick back down and break the double bond between our carbonyl and our alpha carbon, which causes a nucleophilic attack onto our bromine. Water then deprotonates our oxygen atom, giving us our final product. For question 8, the reason why the alpha carbon is on the more substituted side is due to stability. Halogenation under basic conditions, polyhalogenation usually occurs at the alpha position via a nucleophilic attack by an enolate. For question 9, provide a mechanism for the formation of the enolate and then nucleophilic attack on the electrophile, Br2. Our base first deprotonates our alpha carbon, putting a lone pair onto our oxygen atom.
Beat the devil out of it.
Oxygen then kicks back down a lone pair, breaking the double bond and attacking via nucleophilic attack onto one of our Br2 atoms.
Where'd you find this?
Our base, once again, deprotonates our alpha carbon, causing a lone pair to go up onto our oxygen atom, which once again kicks it back down, using a nucleophilic attack to attain another Br atom onto our alpha carbon, giving us our final product.
Beat the devil out of it.
problem, we are given acidic conditions which would cause halogenation to occur only once at the alpha position of our ketone via nucleophilic attack, adding 1 Br to our more substituted alpha carbon.
Damn, son, where'd you find this?
This is then followed by a bulky base which would cause elimination to the less substituted side, and finally is followed up by a Grignard reagent which would attack our carbonyl carbon and put our phenyl group onto that carbonyl carbon with H2O workup would give us our alcohol for our final product.
Real trap shit.
Damn, son, where'd you find this?
Beat the devil out of it.
Get money. Yeah. What? Check this out, right?
Happy accidents. That's the name of the game. It's enjoying. You really ought to enjoy what you do in life. If you do, then you'll do a good job. And that's